Welcome back everyone. We are in chapter 5, flanged section. Okay. I hope we have covered 60% of the beam syllabus in that singly reinforced and doubly reinforced section, and we have described clear cut theory of singly reinforced section, how the beam theory has been derived from the concrete's behavior, steel behavior, how we clubbed both the theories, and then we got the one equation, how that equation is extended to doubly reinforced section. In this chapter we are going to use the similar theory from the singly reinforced section itself. Okay. So if you are starting from this chapter, please look after previous videos, unless you will never understand, or if you have idea of singly reinforced section theory, so it's very easy. Okay. Okay, so we will start with the beam and flanger section. So first the theory, what is flanger beam? I hope you know what is flange and web. Okay, take a T shape. So the horizontal thing is called flange and the vertical thing is called web. I hope you know this one. So what is flanger beam is, if you see the figure, right side top figure, every construction building, every apartment building or every commercial buildings, there will be a beam will be going through at the end of the building or at the center of the building or at the edges. Okay, so edges, if you see the figure, this is called the some portion of the slab. I have to describe it first. You see the left side figure, left side bottom figure, this is the construction site T beam, precasted beam. Okay, they are going to place other section beams brought up here. So to make it clear, consider the shuttering is ready for the beam. They are going to put another shutter and they will place the slab reinforcement also. Nobody will, very rarely they will make a beam casted fully, then they will casting the slab will happen. You see the figure left side, already some concrete beam has been casted. Later part, you see the labor is standing nearby. In that portion, they will bring another precast slab portion. They will bring there. They will couple the reinforcement, coupling the reinforcement. Then they will cast it together. This is called monolithic construction. Okay, half of the beam is precasted. Bringing to the side, they will cast everything in a single slab and beam is casted at the same time. Okay, so this is called monolithic construction. For example, I wish to go back to one of a previous photo. You see this photo in a doubly reinforced section. This can also be considered as a flanger beam, but in this figure, you see in the right side figure, there is no slabs. Okay, since there is no slab reinforcement, there is only beam reinforcement I have shown here. If consider there will be slab reinforcement also, and they will put the concrete at the same time for beam and the slab. Okay, so if they are putting concrete while casting for a beam and slab at the same time, then the beam, there won't be separate layer, right, to separate a beam and slab. So the beam and slab will behave as a single member. You can see the right side bottom figure, there is an initial shape and the bend shape. So if you are designing a beam, considering only it as a beam, the only beam should bend, but you see the bend shape, slab is also bending along with the beam. So some portion of the slab also come along with the beam and it will behave similar to the beam. Okay, so why we have to consider this way? Because so far we have discussed so many examples in single and double reinforced section. In single reinforced section, for a given width and depth and the reinforcement, we saw the maximum moment the beam can take is approximately 100 or 150 kilonewton meter. Okay, in double reinforcement it extended up to 200, 220, 250. In this case, we are having, other than the beam, we are having some extra portion, right, like a flange. You see in the T portion, extra portion is coming to the beam. That extra portion will also take some moment. Okay, so in reality there is no design of beam, there is no design of flange beam. We are considering extra portion of the slab which is casted together will be acting along with the beam. We are taking the capacity of that slab also to the beam, so that you no need to, if somebody customer is coming and asking you to design for a 300, you no need to design for fully 300, because when you analyze you can include some portion of the slab that will also take some 20-30 kilonewton meter extra. Okay, kilonewton meter. Okay, so extra, so that's the major difference. Okay, again I will explain at last. Monolithic construction means casting the beam and slab together so that the slab portion will act along with the beam. Okay, so some portion of the slab is acting along with the beam. Why we need this beam? Because if you are considering only as a beam, the beam can take maximum 50-60 kilonewton meter, means if you are considering the slab also along with the beam, the slab will take some extra moment, some 10, 15, 20 kilonewton meter. So that will contribute to the extra. So you can tell the customer So if you no need to increase the width and depth, considering the slab itself will take some moment. So we no need to increase so it will be economical. Okay, so that is the main concern why the flanged beam came. In flanged beam there are two types. You can see at the right side top figure, T beam and L beam. Intermediate beams can, because the slab will be on the both sides, right? So it will be considered as a T beam. If the slab is on only on one side, it is called L beam. Okay, so both are having a flanges, and web portion will be the beam. Real beam will be the web portion. And don't consider that the beam is at the bottom, slab is at the top. The beam is throughout up to the slab top portion. Okay, the beam is from the bottom to the top portion. Slab will be like our shoulders. Okay, the up to our neck, consider up to our neck the beam is there, the two shoulders will be our slab. Okay, so it's not like slab is above the beam. So the beam will be there from top to bottom, slab will be coming on right side and left side. So that is called the flanges, which is coming extra. Okay, so I hope after this slide you are very clear about what is flanged beam, why this topic came. Also what we are going to do, actually what we are going to do is we are going to analyze, putting some extra flanges, how much extra moment the beams can take. That's what this topic is. Okay, so I'll move on. So flanged beam, this is the, I am taking mostly, I have never experienced L beam that much in the design, so we'll concentrate more on T beam. So this is a simple example of flanged beam. You see this beam, that D is the effective, this is a single rectangle. Okay, so this is a single rectangle, and there is a flanges coming, extra flanges coming at the top. Okay, so this is a nomenclature. BW is the width of the actual beam that will go up to the top. DF is the thickness of the slab which is coming extra. BF is the effective width of the flange. Effective width means I hope to effective width is nothing but this bend shape. How much width of the slab is effectively contributing to the bending. So if you go away from the beam, that won't even bend, that slab will behave with something different, real slab. Okay, so some portion of the slab will bend along with the beam. That's what I told you, that how much is that is called that BF. That's the effective width of the flange. So how to calculate the effective width? Because the slab will be around 3 meter or 4 meter, that will be totally different. So if we are having a slab of 3 meter, so how much portion of the slab will be acting along with the beam? Maybe around 0.2, 0.3 meter, that we have to find. How to find the effective width of the flange? So there are two ways. If the beam are connected beams, means like how I showed in apartment building, that will be apartment building, commercial buildings, all the beams are connected, interconnected. If the interconnected, IS 456 has given a formula to calculate the BF is L0 by 6 plus BW plus 6 into DF. I told you what is BW. BW is the width of the beam, DF is the DF is the depth of the flange, and L0 is the center to center distance between the zero bending moment points. So zero bending moment, you know, if it is a simply supported beam, zero bending moment is at the supports. So if in the question they are asking about simply supported beam, then you should take L0 will be equal to throughout the length of the beam, L0 equal to L. If it is a fixed beam, obviously zero bending moment will not be at the support, because there will be a negative bending moment at the fixed end. I hope you know what is fixed beam. I know about bending. I hope you know bending moment diagram for fixed beam. At fixed end there will be a bending moment. Okay, it is not zero there, and it will be a negative moment. If it is a simply supported case, sagging case, there will be a negative moment at the end. So there will be some zero moment at somewhere where there it will become a positive moment. Approximately IS 456 is recommended to use L0 as a 0.7 times of the length if it is a fixed beam. Okay, clear? So you have to use this formula L0 by 6, where what is L0 I have shown you here. If it is L beam, same formula, instead of 6 you have to divide it by 12, that's it. So L0 by 12 plus BW plus 3 into DF, and it should not be greater than C by 2. C is the center to center distance between. I will show you in the next slide what is C. So I hope what is, you know, I hope you understood what is T beam and L beam and how to calculate the effective width of the flange if it is a connected beam. So if it is an isolated beam is considered a case like bridges. Okay, bridges that the beam will be a single beam. If you see a small size bridge like a 3 meter or 4 meter span length, only to consider canal, you have to cross a canal. Canal length or width of the canal will be around 3 meter or 4 meter. So the bridges will be very small. There they will have only 1 or 2 beams will be there. You can refer Google. So approximately for bridges there will be isolated. It won't be interconnected. So for isolated beam cases, for T beam, this is the formula L0 by L0 by B. B is the actual total width. Okay, available L0 by B plus 4 plus BW. BW is the width of the beam, and for L beam 0.5 L naught divided by L naught, this formula. Okay, you can pass or note it down. These are the IS 456 recommended formulas. If you know these 4 formulas, you can easily determine the effective width of the flange, how much portion of the slab is effectively contributing to the beam. I will show some examples. So question number 18, consider this question number. We are continuing the questions from the session 1, chapter 1. We are continuing the questions. So far we have solved around 17 problems from up to the previous lecture. So from now it is question number 18. There is a footbridge. The slab width of the footbridge is around 3 meter width, and the center to center supporting central supporting beam is of 6 meter length. Width of the web is a beam width is 250 mm. What is the effective width of the flange they are asking? I hope it is clear. So the bridge width is 3 meter and the beam is going at the center, and the beam length is 6 meter. Okay, I hope you can imagine. Width, total bridge width is 3 meter, the beam is going longitudinally in 6 meter length, and the beam's width is 250 mm. Okay, what is the effective width of the flange? So they have given B equal to 3 meter, L equal to, it is an isolated beam, right? It's a bridge. So 3 meter, 6 meter, BW is 0.25 meter. It is given. You just substitute everything here, and as you see here, the check condition is the effective width of the flange you contributing should not be greater than B, obviously, because B is the total width available for the bridge. Your answer should not be, so if bridge itself 3 meter, your answer cannot be 4 meter, right? There is no slab at all. So you got an answer 1.25 meter is the effective width. It is contributing. It should be lesser than. It is obviously it is lesser than the 3 meter. Okay. So please try to understand clearly. The width of the web means width of the beam is only 250 mm. But you see how much contribution is coming from the slab, up to 1.25 meter. From the center, if you imagine 1.25 meter, total width of the slab is contributing to the beam also. Okay, because 0.25 is beam. Okay, that leave that. So 0.5 meter on the right side and 0.5 meter on the left side of the slab is acting along with the beam. Okay, so I hope this example, can you imagine, so far we have never discussed something like this, because some portion of the slab, it's 0.5 meter on the right side and 0.5 meter on the left side is acting along with the beam. That will take some extra moment also, right? So this is a remarkable discovery actually. So I will show you in the further problems how extra moment, how much moment it can take, so that the design of our buildings become economical. So next question, you see this a hall of 10 meter, 15 meter. It is given hall of 10 meter and 15 meter, consisting of number of beams. It is 3 meter center to center. Okay, so it is parallel to short span of the hull. The figure is on right side, you can see. So width of the web they have given is 250 mm, and it is an hall, so it is a interconnected beams. Okay, so thickness of the slab is 100 mm. They have given a thickness of the slab, that is DF. The beams are casted monolithic, so that the columns at the with the column at their end. So they have casted the beam and the slab together. What is the effective width of the flange of intermediate beam? Intermediate beam is obviously it is a T beam. Okay, so they have it is interconnected. So we are using the formula L naught by 6 plus BW plus 6 DF. L naught is given as a, what is a L naught? Give me a second. So a hall of 10 meter cross 15 meter. So it is given beams are casted monolithic with the columns, means it is fixed beam. Yeah, mostly everywhere it will be fixed beam unless they have given. So if it is a fixed beam, we have to use L naught equal to 0.7 L. So the length of the beam is 10 meter. You can see in the longitudinal direction it is 10 meter, and it is so many beams. You should remember the length of the beam is 10 meter. You see the figure. The beam is not this beam. We are not considering the edge beam, right? Edge beam means it should be designed as a L beam. So we are considering the beam in longitudinal direction. The length is 10 meter fixed. So L naught will be equal to 0.7 into 10. It is 7 meter into 10. It is 0.7 into 10. So it is 7 is the L naught. 7 by 6 plus BW is given. Everything is given. You substitute. So effective it is 2 meter, approximately 2 meter. So the beam, if you consider the beam itself is 250 mm only, but you see right side and left side approximately 750 mm, I think 800 mm is contributing. 800 mm of slab is bending along with the beam. That's what it says. 2 meter means center of the beam is 250 mm. Right side 1 meter, left side 1 meter is bending along with the beam. So this is the effective width of the flange for this case. Okay. So in the same problem, if they are asking the beams are simply supported at the end, means what will be the difference? Okay, so if it is they are asking for end beam also, I think effective width of the flange of the end beam. So end beam means L beam, right? At the edges it will be L beam, first thing. So we have to use different formula. L naught by 12 we should use, plus 3 df will come, and if it is simply supported we should take directly L naught equal to 10 meter, just substitute everything. So if it is L, you can see 1.38 meter is the total effective width of the flange. Okay, so this is, I think this will be enough for I hope I have shown you how to calculate the effective width of the flange for different practical cases. Okay, so this is very important. Unless you don't know BF, next is how to analyze the other things will be very difficult. Okay, so with this I will stop this session. Okay, so next section will be how to analyze a T beam. Okay, how to analyze, if somebody is giving you this is the dimensions of T beam, how much moment it will take, I will tell you how to analyze. Analyze means how much moment it will take, how to calculate. Okay, and we will solve some 2-3 problems. Okay, so thank you, we will see in the next session.